All right. So yeah, we talked about ice tables yesterday. That's kind of what we've been gearing up to for a few classes with equilibrium constants. And we learned that having an ice table is a way to go from a starting concentration to finding the equilibrium concentration. And so really that's the primary goal with these ice tables is we want to be able to find an X value that we can then plug into the ice table in an equilibrium row to see what the concentration is of these reactants or products, because that can be really important for different things. And you'll see in the next few weeks that once we start talking about pH and acids and bases, being able to have that concentration of an acid or a base is really important because you can find the pH or the pOH and all that stuff. But I think that's a little bit later in this unit. So you have some time before that. But does anyone want to be brave and say what they think the difference between K and Q is? Yeah, anything else. Yeah. And Q could be at equilibrium, and that'd be if Q is equal to K. But you kind of have to plug in the data to figure that out. Real quick, we can go over this. It's kind of a thing I think he talked about maybe on Monday, where if you want to see where the reaction is going to go based on Q to see if it's going to go forwards or reverse, or if it's already at equilibrium, you can always write it K first. So I think of K comes before Q alphabetically. So if K was less than Q, turn this guy into an arrow, and that tells us we're going this way. So we're going towards the reactants. So if K is less than Q, we're going to start favoring the left side of the reaction, meaning we're going to favor, there's a few ways we could say that. We could say we're favoring the left side, we're favoring the reactants, but probably the most common way you're going to hear it is we're favoring the reverse reaction. Same goes for K is greater than Q. We can do the same trick. That was a lot worse, but we're going to be going forwards. It's really blurry right now, but we'd be going towards the reactants in the forward direction. And then, of course, I already said it, but sometimes you'll find that when you're solving for Q, it's the same as your K. And that basically is saying, hey, look, we're at equilibrium. We're not going to be going one way or the other because we're happy where we're at. So that's kind of a review about what Q is. And yeah, we can get into, I think this next one is maybe this one might not be an ice table yet. Let's read it. So we say at equilibrium, a system has 1.5 liter gas sample taken at 25 degrees Celsius. Who knows if we're going to need that data? Sometimes they throw in random numbers. And that gives us the values of 2.55 grams of SO2. Here's the molar mass of SO2, 0.115 moles of O2, and 0.350 moles of SO3. So I gave you a lot of numbers there. And the first thing I'm asking you is what is Kc of this reaction? So right off the bat, I'm not necessarily thinking we need to use an ice table. And one of the ways I can tell that is because they're telling us that these concentrations or these masses, whatever they gave us, are already at equilibrium. So the times when we do need to do an ice table is if they say we're starting with this amount, or you have this many reactant, but we don't know what's going on at equilibrium. That's when you have to do a whole table. So the way I would go about solving this is I would probably figure out what the K expression needs to look like, and then figure out how we can get molarity values in all those parts. And I was kind of annoying because I didn't give you it in molarity, and one of them I even gave it to you in grams. So you got to do a few steps. You're gonna have to go from grams to moles, and then put that over volume to get a molarity. So spend a few minutes working on this one. I think this is a good review before we get into ice table stuff today. And you get a KC value for this. Here's what I did. So again, I used the 1.5 liters as our volume of solution. And don't be thrown off by the wording if that was kind of weird because it said like gas sample, but um, imagine that made more sense. I don't remember why I wrote it like that. But we find the molarity and then we can plug it into the K expression. And remember, we always need to still use those coefficients when we're setting up K. So this is going to be squared and this is going to be squared. Again, it's always products over reactants. And then once I plug in those values, this is kind of what I got. Simplified it down, it ends up being right about 1,000 or 1.01 times 10 to the 3. And so we have KC now, and now we can use that to do this next problem. Again, I think this is something you did maybe even last week, but there's a formula for going from KC to KP. I can pull it up real quick. This is one that I always forget for some reason. Here we go. I'll write it down here. KP, and again, KP is another, it's also an equilibrium constant, but we're talking about pressure, so that's going to be atmospheres most of the time. Whereas KC is concentration, and we have RT, raised to the power of delta N. What is delta N again? That's the one thing from here that is easy to sometimes forget. Moles of, you almost got it, but be a bit more specific. N is talking specifically about moles of gas. So you basically got it. In fact, on this one, they're all gas, so you probably would have gotten the answer right anyways, but sometimes there might be a solid or a liquid in there, and you don't want to factor that in. So it's moles of gas in the products minus moles of gas in the reactants. So in this case, I see 2 moles of gas in the products and 2 plus 1, so 3 moles of gas in the reactants. So the delta N is going to be -1 on this one. Yeah.
Oh.
We'll spend a few minutes working on that one. And also, again, this R is going to be the one we used on the first unit, the 0.0821, not the one that you guys used on the last exam. Is that what you guys got? 41.3. So that one, again, should hopefully be some free points on the test when you see that formula. All you're doing is plugging it in. Next one, let's see, if a sample was taken before system reached equilibrium. Sure, we can do this one real quick. I don't want to waste a whole lot of time on it though, because it's kind of doing the same thing as what we did on the last one. But basically what this one's asking is before we reached equilibrium, we took some samples at that point. What does that sound like? If we're not at equilibrium, we're solving for Q. Yep, so this is basically we're solving for Q, and then this is sometimes how it's going to work is you solve for Q and then you go back and find out what your K was, and then the question is going to be asking, are you going forward? Are you going backwards? Are you at equilibrium? That sort of thing. So spend a few minutes working on this one, but really it's the same process as what you did up here. I think so. Yeah. I would look at the formula sheet on Canvas to make sure, but that doesn't seem like one that you would make you memorize. But if you do have to, it's not that bad. So this is what I got real quick. 97.4. And so we'd go back and compare that to the K value. And so what do we think? Is the reaction going to proceed forward or reverse? Are we at equilibrium? What do we think? Forward. Yep. We can go back up to this thing up here where we set up K and Q, with K always being the first thing. K is greater than Q in this case. And so we're going to be going towards the products or in the forward direction to get to equilibrium. And then, yeah, I already answered this. If Q is equal to K, that means we're at equilibrium. I'm going to skip this one, to be honest, because I think you guys are good with this stuff. This is the exact same. I don't know why I put so many in like this. Let's go down to the stuff that is new. So I can post this in the answer key later if you want extra practice. But here we have a reaction set up as A going to form B plus C. And we're given the equilibrium constant, Kc, as 1 times 10 to the minus fifth. First off, if we're thinking ice tables here, what does that K value tell us? Or what can we use that for? If it's 1 times 10 to the minus fifth. When I see that for an ice table, I'm thinking 2 thumbs up, right? We can do the approximation. So that's always my first thought here. But let's keep reading. So if you start with an initial concentration, again, that's another kind of clue in that we're going to be doing an ice table here, where we have 0.1 molarity of the reactant A and no products. Sometimes it'll say outright, like in this problem here, that you start with no products. Normally that's assumed, so it might not even say that part. And I'm asking you to calculate the equilibrium concentrations of A, B, and C. So see if you can do this on your own, and then I'll walk through it up here as well. So I'll kind of finish off this one. We have, again, setting up the K expression as we always do with products over reactants. And here's how I set up my ice table. We're starting with a certain amount of reactant A, the 0.1, and there's no coefficients here, so we don't really have to worry about anything too fancy going on here. So it's going to be minus x plus x plus x. And then we always plug in these terms straight into the K expression. So that's going to look like x times x over 0.1 minus x. And what we said is that this value is sufficiently small that we can say that anytime we're really adding or subtracting x, that's not going to make a difference. And a lot of times people ask me what number is kind of like that mark of, greater than this is not small enough, lower than this is small enough. I normally say if it's 10 to the minus 3 or smaller, that's a good kind of rule of thumb. He's not going to really give you anywhere it's super kind of on the fence of like, I don't know what method to do here. So normally it's going to be a number that's like this small. But yeah, so we get rid of the minus x, and now this becomes a lot easier. Uh, it's pretty simple to figure out how to solve x here. We're going to multiply by the denominator on both sides. Let me do that real quick. And then this is x times x, so we really have it as x squared, so we can take the square root over here on both sides. And this is how I take square roots, by the way, or cube roots. I use the little like caret on my calculator and then put in parentheses 1 divided by 2. And so we see that x is equal to 1 times 10 to the 3. And it's very possible that he would give you this as an answer. And oftentimes that's not what they're asking for. So this is x. What we need to do now is plug this back into our ice table. So again, the goal of an ice table 9 times out of 10 is to find the concentration of these reactants or products at equilibrium. And so for B and C, if they were asking about either of those, x would be our answer, right? Because all that we have here is an x. But if it were asked for A at equilibrium, we have to do 0.1 minus x. So it's going to be 0.1 minus 0.001. And so A is 0.099, which is basically 0.1. And that kind of goes to explain why we can do the approximation in the first place. And then he has a method that I think maybe talk to you guys about of like how to make sure that your approximation was valid. Does that ring a bell? Okay. To be honest, I've never done that in my life. Like I said, he's not going to give you stuff that's on the fence. And on a test, you don't really have the most time in the world to do that. So you can kind of assume you're good to go if you see a small value like that. But let's go to this one because I think this next one's a little bit trickier. And to be honest, if you can do both of these, you can kind of do every ice table that he's ever going to give you. So he's very nice. He doesn't make you do quadratic formula or anything like that. So this next one, though, spend a few minutes working on it. You'll see the big difference here is that K is 0.5. And that's a number that's definitely not small enough for us to do our cool trick. So All right, keep working on it if you got it, but I'll kind of go over my process up here and finish it off with you guys. So here's how I set up my ice table again. Um, we kind of assume we're starting with no products here, and so we have to be subtracting from the reactant side, adding to the products, you know. But we have to remember that when we have a coefficient, it's going to be factored in two different times. So it's going to be in this part, and it's also going to still be the exponent in the k expression. So that took me a long time to understand that like the coefficients play a role two different times in the process. We have 0.3 minus 2x, x and x. And so we set up our ice table and we said that we cannot approximate the minus 2x as being insignificant. So what we do here is, because it's friendly and they make it nice for us, we have something where it's something squared in the numerator here and something squared in the denominator here. So what we can do is take the square root of both sides, and then it becomes a lot nicer. So square root of 0.5 is 0.707. And now that's equal to x over 0.3 minus 2x. Let me get some room over here. Whatever. Again, we have 0.707 equals x over 0.3 minus 2x. And so we're going to multiply by the entire denominator on both sides. And then this is like, you can't even see that. Okay. This is like the FOIL stuff that you maybe learned in middle or high school, where this guy has to be multiplied over here and over here separately. So let's do that real quick. So 0.707 times 0.3 is 0.212. And then we still have the minus sign here. And so 0.707 times 2x becomes 1.41x. And that equals x. So now we can do a little bit more algebra. And this is a step that sometimes I get thrown off on. So what we have to do here is you always want to think about having your variable on the same side. That's the goal. So how can we get this guy over here? We can do that by adding 1.41x to both sides. Oh my God, I keep messing up decimals. And another thing that I often mess up on is I forget that the x has an invisible 1 in front of it. So adding the 1.41x, it really becomes this plus 1, so it's 2.41x. A very easy mistake to make, but there we go. Now we have this, and we can do some good final steps to get that x by itself by dividing by the 2.41. So that's some good review of algebra. Yeah. Yeah. Um, I was a little bit rusty. I remember when I had to relearn this stuff from whenever I took algebra in high school. So definitely practice that a good bit. But again, the final answer is not x by itself for all of these. So in this problem, I told you calculate the equilibrium concentration of D, E, and F. E and F, it is nice, that's x, but we have to do 0.3 minus 2x to find D. So let's do that real quick. 0.3 minus 2 times the 0.08. Make it call it 0.088. That's going to be 0.124. So this is the concentration of D at equilibrium, and then 0.088 is the concentration of E and F at equilibrium. Do you guys feel good about that? Do you want me to review any parts of the math there? So again, over here, all we did was just multiply this out to both sides. Come over here, add the 1.41x to get x's on the same side, and then divide. So we can isolate that variable. But yeah, if you guys feel good with this, you're in a very good spot. I think Dr. Bowman does it really well, kind of starting slow with ice tables, but I can stop sharing now.